we're rolling. Start out with any questions? Well, that's easy. Okay, we're going to be doing a lab today. I have it printed out for you. So I want to talk about some of the background here and the fact, and if you get stuck, if you go to the course, at this point everyone's done the course entry assignment. If you go to labs, it'll be the available lab. But you're going to have styrofoam hanging on a string, and then you're going to charge the styrofoam and you're going to charge PVC. You're going to put PVC in the same spot every single time. In the lab itself, I have a diagram here, and I put 15 centimeters away. It's not necessarily going to be 15 centimeters. That was specific to the video, so whatever it happens to be. You'll have a meter stick down and it will be on some set position. Because they're both going to be charged the same way, by using rabbit fur, they're going to repel, and so the styrofoam cup will be pushed away. Let's go through the method. For those who haven't had me before, I call it the facades method. It's basically the mnemonic for solving almost any problem in physics, or at least in 151. So, force diagram, we have these three forces acting on the styrofoam cup. This one right here. We have the electric force, the tension, and the weight. It should be in equilibrium, so A is for acceleration. There is no, acceleration is 0, and properly should be meters per second squared or some sort of unit. So we can set up a coordinate system however we wish. The coordinate system that we probably should set up if acceleration is 0 is one that will require us to break up as few vectors as possible. And so if we go to traditional horizontal vertical, we only have to break up one vector. And if this angle here is phi, this becomes the tension cosine phi, tension sine phi. So this is the decomposition. So force diagram, acceleration, coordinate axes, decomposition, the equations of motion, plug it into F equals ma. Since A is 0, we just have mass times 0 on the right-hand side. Left-hand side, we've got Ft sine phi is minus the weight is equal to 0. And horizontally, Ft cosine phi minus the electric force is equal to 0. Substitution, we have a formula for weight. We have a formula for the electric force. And then comes to solving it. If we divide this equation by that equation, so we divide the left-hand sides and divide the right-hand sides, we get sine phi over cosine phi, which is tan of phi, and then mgr squared over k q1 q2. Just rearranging it some to go more towards what you get in the lab is you have basically flip both sides and then multiply both sides by r squared, and we get this. So if I plot that versus this, so I have an r squared over tan phi, and then I have a q1, q2 over mg. Well, if I put it into math terminology, that's y is equal to slope x plus b. Because ultimately I wanted this form in order to do analysis. Is this in the way?
No, it's fine.
So that's my vertical, or my y, r squared over tan phi, and this is my x right here. So that must be my slope, which should be somewhere around 9 times 10 to the 9th in SI units. And my intercept should be 0. Now, it's physics. What are the chances? I did do this a variation of this lab a number of years ago, and no one got a particularly good value. So this is not one where if you're off by 100%. Yeah, it's possible you did everything you're supposed to do and still are 100% off. But I looked at the class average. So I basically took every group's value for K, and it came out within 5%. So it can get good results if you take your time and don't make a careless error. If you're off by a factor of, say, 10 to the 9th or 10 to the 18th, you probably have a unit issue. And the unit issue is going to come in the fact that my value for K here is going to be, let's see if I can draw it, lowercase k. My electrostatic constant is going to be approximately 9 times 10 to the 9th Newton meter squared per Coulomb squared. But when you measure the value of the charge, it's going to be in nanocoulombs. So you've got a factor of 10 to the negative 9th built into what you're measuring, and you need to take that into account at some point. So in the tables, I have you recording it in nanocoulombs, but when you are getting to this last table here, it's in coulombs. So please make that transition. So a nanocoulomb, 10 to the negative 9th coulombs. Now I have the various values here, so let's talk a little bit about that. Mass, triple beam balance, finding the mass of the styrofoam cup. Electric force, Q, the charge, we have charge sensors, and in essence, you're going to have some sort of metal hooked into the charge sensor. And then that's going to be hooked to a ground. Large object. Large conducting object. Looking into a piece of wood doesn't really help a lot. I've done this lab over at the Transportation Center, and all the tables were metal, which really messed things up. It makes it more difficult. We don't have that issue over there. The tabletops over there are not conducting, so that's good. But you still need to hook it to some object, presumably far away. Now, you're going to take the cup, charge it up with a rabbit fur, you dip the cup in, you take it out, you dip it in, and what you're going to see is that if you zero the sensor, you'll have 0 there, it's going to be cruising along, you dip it in, it's going to drop down, you take it out. It's not going to be quite where it was before. It really depends upon the humidity and other factors. If you touch the sides of this metal, and then it's going to dip down, and then eventually as you dip it up and down, it's going to come out to be roughly the same in and out. That's the point where you care. Then you do the other one, the PVC, dip it in and out until you get it sort of at a steady state. Then you have the readings. You take the PVC and place it wherever you're going to place it, see how far this thing goes, and measure that angle. Phi is the angle down here. You'll calculate phi once you know theta. The advantage of doing this now, as opposed to midsummer, is in midsummer, the speed at which you need to do the measuring of the charges with once you've charged it to actually getting the final measurements has to be done within about a minute. You got a little bit more leeway because it's not as humid, so we're going to have less charge bleeding off into the air. However, don't dawdle. It's not when you're starting out, yes, the first one might take a while, so you might have to redo it. But at some point, you can't just charge it and go, all right, so what do we have to do next? Because you're losing charge as you do that. Another thing to keep in mind is that there is a maximum limit on this, that it should not be less than negative 70 nanocoulombs or more than 70 nanocoulombs. It's somewhere between 70 and 80 where you're maxed out. So if you have 120 nanocoulombs or negative 120 nanocoulombs on it, then it's gonna read like 70 or 80. And if you start writing those numbers down, you're already building in a huge loss. So if you have too much charge on it, so you put it in there, it pegs out, you're obviously clearly going way past what it can measure. If you touch it to a piece of metal, you lose some charge. So if you just touch it to the can, that'll take some of it off. Questions before I talk a little bit about how the charge sensor what this charge sensor is actually doing? All right. So when I have the can here and I take the piece of PVC, I dip it in, what's happening is that the charge sensor is measuring the charge that's flowing one way or the other. So if this is negatively charged, then electrons are going to flow this way from the can itself. And so when the electrons flow, it's measuring this electron flow here. So it's not officially measuring what is on here, it's just measuring the reaction to it. So if I've got a pie pan, a shallow pie pan like that, and I just put the meter right here, it's not particularly close. What the electrons that get chased off of it is not really an indication of the electrons on here, or the excess on here. Ideally, you have a narrow piece of metal, and you're putting the PVC or the cup as far in as you can, because that's going to be the best way to get the measurement. So if you're using a pie pan, feel free to sort of fold it up so that it looks more like a cup. And we have pie pans. We have metal cans also, which I've used in the past. Although that works fine for the PVC pipe, it's a lot harder for the cup, for the styrofoam cup. All right. I think we are ready. If you do not know how to write this up, in other words, don't repeat units, group name needs to be the same. I think there's enough people in here who have gone through this that, one, you can ask, and two, if you haven't watched the lab videos, the 2 lab orientation videos, you need to do that. So we're gonna head down to the other room. And 3 pages, and of course it's not collated particularly well, but I would say grab your lab on your way. And I will go first turn this off and then unlock the other door.